me just check my audio here. Seems good. Okay. We're looking for my mouse. All right, so we have started our discussion on antiderivatives. Let me just get a better pen here. That one's nicer. Antiderivatives, where we're given a function. Now it could be called anything. I'm just emphasizing that it's the derivative of something. I don't necessarily know what the function is. We want to find the original function that can give me rather that derivative. This is an antiderivative of my original function. Now it doesn't matter what I call that original function. For example, I can call it f of x. Let's suppose that is simple as possible. Let's just say 2x. Then we say the function, call it whatever you want. I'm not even going to give it a name, to be honest. X squared is an antiderivative of 2x. The name is quite irrelevant. Initially, we use this big F to help remind us that yes, we are starting with a derivative now and kind of working backwards. But the names are irrelevant. I don't even have to say this. My sentence here is complete as it is. X squared is an antiderivative of 2x. Now, to be more complete, we realize that I can add or subtract something, and still, when I take the derivative, I'll get 2x as my target. So more complete, I'll say x squared plus c is the family of antiderivatives of 2x. So after our initial introduction to the concept, we are really focusing on this sentence and what that means. Now realizing that I am not really attached to any specific name for these functions, f, big F, small f, prime, not prime, it doesn't really matter. I have let go of that now, but I still want to have a name that's a little shorter than this sentence. Really just this is still sort of half English, this sentence. I want to represent this sentence with a mathematical sentence. So fully mathematical, I'm going to say the exact same thing. It's very important to realize that the the representation that we're going to give next is exactly the same as this sentence in the square box. So I want to, just like originally in the question, I'm starting with 2x. So 2x is given, for example, and I'm looking for the antiderivative. But instead of saying the antiderivative of 2x, so let's have a little sentence here to have the order exactly the same. The family, but I'll just say antiderivative of 2x, I'll say here with obviously x as the variable is x squared plus c. That's our sentence we were trying to translate. And I want to emphasize that this is simply a translation. We're not doing anything. So the squiggly portion of that sentence I will represent by a long stretched out S. The curly portion, x as the variable, I will represent by a dx. I need to know what is the name of the variable in question. Because in more complicated situations, there could be other variables here and there's a mix, and I need to know what am I focusing on. The double squiggly line will be my equal, of course, and then the jagged lines will be my answer. So in the circle there, well, not a full circle, in the circular area, that is going to be my mathematical version of the translated sentence. The sentence means the same. We're going to call this symbol the integral symbol. And we're going to call this whole thing, this sentence really, or called the indefinite integral of, in this case, 2x. Really, I'll say here with respect to x. Now, when I only have one variable, it's sort of implied what the variable is, so I don't have to say that bracket portion, but I do in this mathematical representation, I do need to have my integral symbol telling everyone we're looking at antiderivatives and my dx, or the d with whatever the variable name is, to indicate that x is my variable and nothing else. All right, so that is the indefinite integral. Now, why indefinite? Because there is another version of this integral, still connected to antiderivatives, but we're going to have to wait a while to introduce that. There's a comment here that the stream keeps cutting in and out. If that is the case, I'm assuming YouTube. If YouTube cuts out, I am sharing the screen on Discord as well, which shouldn't have any delay. I'll just type it in here. Yeah, it's really struggled to load for some reason, even though my internet connection is the same as always. There's no indication of why it's doing that at all. And I finally got it to run, but I can't even see a preview. It does say excellent connection, like always. So on my end, I can't see why it's having any issues. But if there Uh, if it's continuing, remember that I am recording it on my computer as well, so I'll put that video extra on YouTube, which won't have any issues. So I apologize for any technical issues that you're seeing. I really can't see, it's not giving me any indication of why it's struggling. It could just be a general internet issue, though it says excellent connection and it's not giving me any issue. But I am recording it as well as a backup. So you can try, but if it's not getting any better, I did try and restart my device and everything. Nothing seems to be working. So it's just one of those days. But I am recording it, and right afterwards, I will put that up in the playlist as well. All right, so I'll keep going for the video's sake. I apologize if you can't quite follow it along. Let's have a look now with this new notation. What is the difference? Let's look at this very bottom one, 15, in our antiderivative style. So I have negative 4 e to the 3x. Now previously we gave it a name, negative 4 e to the 3x. We gave it a name and we then said, okay, the original function that would give me this as a derivative, let's build that answer. I keep my negative 4 out of it. Now I'm interested in e to the 3x. Well, the only thing that can come from is e to the 3x itself. But if I leave it like that and take the derivative to check, the chain rule is going to give me as the second part the derivative of 3x, which is 3. And there's no 3 in my target. So I put a 1/3 in front so that when I take the derivative, everything that should cancel, and I get my target. And then, of course, I add the plus c and so on. So nothing changes in what I'm doing. Now, my new way of writing it, there's no difference here at all. It's just a new way of writing it, which enables me to not care about names of functions. I am given my derivative function. I'm looking for what is the original that would give me that. And we call that the indefinite integral or antiderivative of this with x as my variable is exactly the same thing. Literally nothing has changed other than the appearance of my sentence, of my answer. So it's merely there for convenience, merely there for convenience. So we are just trying to get used to this new representation of the exact same thing as yesterday. And we happen to call that the indefinite integral. So if, for example, are these exactly the same? No. No, they're not the same. Let's do number 8, for example. Square root of x plus 2 over root x. So, sorry, hold on. 12, 12.2. 12.2, 12.2, number 8. I'm looking for the indefinite integral of the square root of x plus, I can't remember, 2 over root x with respect to x. So just to emphasize, I'm never going to have just the integral symbol and not the dx. I'm, for our purposes, never going to have the dx and not start it with an integral symbol. they are always going to be together, wrapping like brackets do the given function. So I see people in tests being a little bit too sloppy, even for our liking, writing an integral symbol and not finishing and not closing the bracket, or not having an integral symbol but having the x's there. Now, later on, we're going to do a little shortcut like that, but for now, think of it as brackets, a container for my given function. So now I can say, okay, well, I don't like the look of these guys. Just like before, I prefer to look at x to the 1 half and a 2x to the negative 1 half. And of course, I wrap it like always, or from now on. Then my argument's the same. I'm building an antiderivative. Everything is the same. So when I look at x to the 1 half, I'm trying to see what could that have come from. Well, it has to be x to the 3 over 2, so that when I take the derivative, my power rule is going to decrease that. I'm going to get x to the 1 half. But if I leave it like this, I am going to get 3 over 2 x to the 1 half. So I do get my x to the 1 half, which is very important. I just need to fix the number and tweak it a little bit so that I get exactly my target. And that's going to be by putting a 2 over 3 with it, so that when the when the 3 over 2 comes out in the power rule, I catch it and have only a 1 in front of the x to the 1 half. Then by the sum property in reverse, I can look at the terms separately. I don't love the 2 there, so I just keep it in front like the constant times a function property allows me to do. And then I focus on x to the negative 1 half. Well, reversing the power rule, that's going to have to come from x to the 1 half, because the power rule is going to decrease the power of x by 1, giving me my desired negative 1 half. But if I leave it like this, there's going to be another half popping out, and that's not in my target that's given. So I put 2 there, so that when I take the derivative, this 1 half will go in front, the 2 will catch it, they will cancel, and I'm only left with that 2. And of course I add a plus c, like always, because I am really having a family of antiderivatives that are essentially very closely related. I can't have any other x's floating around, but they could differ by a constant, because when I take the derivative, the constant will become 0. So nothing has changed. We're just practicing this derivative properties in reverse concept. Let's do a couple more. So let's have a look at, it doesn't really matter. How many do we have? All right, we have some. Let's do, hmm, let's do 14 maybe. 14. I'm looking at the indefinite integral, so I know antiderivatives. X cubed plus cube root of x. X cubed plus cube root of x over x squared, and my variable is x. So my integral sign and my dx wrap the given function. So now we mentioned yesterday that even if it exists, I do not want to mess with reversing a quotient rule right now, or really ever, to be honest. So I want to rewrite this to try and get basic properties up to the power rule. That I can handle. So I'm going to split the common denominator, x squared, and then simplify each term, x. And this guy here is x to the 1/3, the cube root of x. So when I move the 2 up, it becomes a -2. So I have here, let's just highlight that because I know some people struggle with that. It'll be x to the 1/3 minus 2. So 2 is 6/3. So 1 minus 6. So I have x to the -5/3. And of course, I wrap that with my dx. Then I think we can squeeze it in here because I've sort of used my space there. All right, so I have a target of x, which means that's going to come from x squared, but I need to correct a number because if I leave it like that, I'll get a 2x, and there's no 2 there. So I need to put the reciprocal in front to catch that and give me exactly my target. For the other one, it's going to have to come from x to the power of what? It's going to be one more. So it's going to have to come from -2/3, so that when the power rule comes in to take the derivative, I get a new power of x that's 1 less. My target is -5/3. But there's no extra number here, just a 1. Yet the power rule is going to put the -2/3 in front. I need to catch that. So I'll do a -3/2 in front. And of course, plus c. So nothing has changed in the concept. It's just more practice and writing the antiderivative question or antiderivative sentence by using what we call this indefinite integral. So let's keep going. Which one should we do? Let's do number 10 to wrap it up. I'm looking at the indefinite integral of 2x plus 1, x minus 2. 2x plus 1 times x minus 2. And of course, x is my variable. So now, again, we don't have any reverse product rule or anything that we've seen so far. Even though that exists, I'm trying to keep things as simple as possible. And foiling this out first will put me in a better, simpler position. So I have 2x squared I have an x for the inside ones. I have a minus 4x for the outside ones, so minus 3x, and then I have a minus 2. And those are straightforward again. So I need to get these basics down. I can't rush forward to slightly fancier concepts if I don't have the basics down. And these basics, apart from how we're going to represent the antiderivative sentence, these basics completely rely on my comfort level with the derivative properties. So there's really almost nothing new here. I just have to use them in reverse. So the antiderivative for 2x squared is going to be, keep the 2 in front, x cubed with a 1/3 correction. Make sure that dot is nice and clear. It's not 2 1/3, it's 2 times 1/3. Minus 3 stays in front, x squared is needed with a 1/2 correction. Then another minus, that one will be 2x. Now I will note here, in case someone that watches it later has a question about that, technically I'm looking at the antiderivative of the first one. There's a c there. There's a c for the second one. There's a c for the third one. Those c's are not necessarily the same. I don't know what constant they could represent. I don't really have more information to know exactly which antiderivative you're looking for. That's a number, that's a different number, that's a different number. I'm just going to pool these together and put a plus c at the end, where c is the sum of all the constants that pop out, because I don't know what they are. If I eventually get more information, which we will, and I have numbers for each individual one, then I would necessarily have a number to add at the end. So there's really no benefit in thinking of individual constants when they will always merge into one constant that I can just put at the end. And we'll call this the integration constant. So there's always what we're going to do. There's never any need to worry about constants on the way when I can always just pool them and represent them as a single constant. All right, so hopefully at this stage we have our antiderivative indefinite integral concept pretty well settled, and we can build on that. Now we are going to take it one step further because we realize that there are other kinds of situations. We could have more complicated derivatives to reverse engineer, so to speak. For example, before we worry about the problem book, let me just try and illustrate by example how these are different. If, for example, I have x squared plus 1 times x, and I'm looking for the antiderivative of this. Given our experience up to this point with this new chapter, what would we do? We would FOIL it out or multiply the x in and then have a simple basic properties and power rule issue to reverse engineer to find the antiderivative, no problem. But it's only convenient because the bracket is just on its own. What if I have this bracket to the power of 10? Now foiling this out is something that I just don't want to do at all. I'm just going to make it a little bit nicer and put a 2x there for no reason whatsoever. Now, yes, it's still possible. I could still foil this out, but I really don't want to. Isn't there a better way? So for now, we're going to guess and check our way through this to just get the idea across. Guess and check. Because I'm just reversing derivative concepts I already know, it's not a, a ridiculous strategy to just guess and check my way through this. I'm going to guess that I'm going to need x squared plus 1 to the 11. I'm going to have to get that. How else am I going to get this bracket to the power of 10? Now I see this is a function of a function. So I'm really trying to reverse engineer the chain rule, which is a more complicated derivative property, but one that happens a lot. So I'm trying to build up to a way to handle reverse chain rule situations. So now if I leave it like this, I'm going to have to check because it's a guess and check strategy. I made my guess. Of course, the constant is irrelevant for my checking. Now I need to check. I made my guess, so it's check time. So if I see how close am I getting with this guess, let's see. Well, in doing this check in the derivative taking process, it's a chain rule because this is a function of a function. So the outside function is something to the 11. The derivative of that is 11 times the something to the 1 less. And you see, I get the target or part of it that I'm looking for. There is no other way really to get it in any convenient way. Why is this 2x there in the target? Well, because there's a second part of the chain rule. And that second part says take the derivative of the inside function, which is 2x. So if that 2x wasn't there in my target, this would not have been a good guess. I do need to fix this 11 because there's no 11 over there. So I put a 1 over 11 in front to catch it when it comes out so that that's only 1. So some things are familiar. Still the number correction. Still need to check if the numbers are what they should be in my target. But there's also now a chain rule situation that I need to be aware of and sort of reverse engineer this. So my guess was almost complete. Just needed to put the right number in front to make sure the numbers in my target will work. So we are taking initially a guess and check approach to reversing the chain rule. And that's all I want to do today. Just getting used to reversing the chain rule and why there are two things in my target. Because the chain rule creates two parts. So when I come up with a function of a function as my antiderivative answer, the derivative target that I'm aiming for should have two parts. All right, let's make some space here. it's very important in the beginning to not go too fast. People rush through this reverse chain rule way too fast. It is not easy, but eventually it will become more straightforward. Our guess and check strategy will evolve tomorrow into something that has more of a stepwise procedure to it that will make it a little bit easier. Right now, I'm just trying to get used to what the antiderivative, what the question looks like, what this integral has inside it, and why. If, for example, I have e to the x squared times 2x, so what I see in my integral is some part is a function of a function, and there's some other parts as well. So when I reverse the chain rule, I'm not looking for the whole thing being a function of a function. But usually, almost always for us, some part of it will be a function of a function. And there will be some other parts as well that we'll see are kind of needed. So, guess and check. Guess, and then we'll check. Now, many people like this guess and check strategy so much that that's all they do. And they can sometimes get away with that because the complexity of questions aren't our questions aren't that complicated, but this is only an introduction level strategy. So, what could give me e to the x squared? I don't have much choice. It's going to have to be e to the x squared. There's not much I can do. So, in my check, I'm going to see how close does that get me to my answer. How close? And maybe there's just a small adjustment to make, maybe not. We'll see. Just want to get an initial guess. What is the essence of the function going to have to be to get me this function of a function portion in what I see? And because it's e to the something, it's going to have to be e to that something. But now I have a function of a function in my derivative to check. And I'm back to the early chapters, derivative, chain rule, nothing strange. So it's e to the something. The first part of the chain rule says take the derivative of e to the something, which is e to the something. Second part of the chain rule says take the derivative of that something, which is 2x. And I have my target perfectly. This one gives me some part of it. Second part of the chain rule gives me another part of it. There's no adjustment needed. I am done. So many people are bothered by the fact that the original antiderivative question, the original target that's given, has multiple parts to it, and not all of them are functions of functions. Some of it is a function of a function, some of it's not, and that bothers them. But I'm not doing the chain rule. I'm trying to reverse engineer the chain rule. So my requirements are different. A hint that this is what's happening is when I see some parts being a function of a function. Maybe all, but it doesn't have to be. And it won't work if this guy isn't there. It won't work. I need that 2x there in my target, or this won't work. For example, let's note this. I have a whining cat in the background. Let's suppose I have this without the second part. Now you might think, ooh, chain rule. Yes, but I'm not taking the derivative of this. I'm trying to reverse engineer the chain rule. So you could have a guess and say, okay, well, this is going to have to come from e to the x squared. I have no choice. And then my check, now I take the derivative of e to the x squared. Well, I leave some space because maybe there's a correction needed or something. Take the derivative of that. I see, well, this is a function of a function. Taking a derivative is the chain rule. So it's e to the x squared as the derivative of the outside function times the derivative of the inside function, which is 2x. And now I see, oh, but there's no 2x in my target. There's no 2x here in the integral question. So, oh, why don't I just put a 1 over 2x in front so that it then cancels. What is happening to this cat? So that it can cancels and I'm good to go? Hmm, I'm not sure. Because this isn't correct anymore. I have now put something in front of my e to the x squared that is not just a constant. So it's not the constant times a function property anymore. I can only do that if I have numbers in front. Now I have x's in front. So this will have to be the derivative of e to the x squared over 2x, which is the quotient rule, because I've now put more x's in. And the quotient rule is going to give me a whole mess of stuff. Derivative of the top times the bottom minus the bottom times derivative of the top. It just is not the same anymore. I I got further and further away. I can't make corrections, I'll call it, or adjustments with x in it. I can only correct numbers popping out by a power rule or something. I can't make corrections with x's. So this, in fact, it can't be done. Can't be done. There is literally no function I can write down that is the antiderivative of e to the x squared. It cannot be done. I need the 2x to reverse the chain rule. I need to see the second part of the chain rule to make a function that's a function of a function as the original function, because when I take the derivative, the chain rule produces two things. So that is my target. I need to see two things when I reverse engineer the chain rule. So there are some things to think about. You can practice you can practice 12.1 and 12.2 kinds of questions, which which are pretty much the same regardless of how I write them. I'm asking for the indefinite integral, asking for just an antiderivative question. Uh, it's the same. It's the same thing of basic antiderivatives. And we'll continue our discussion on the chain rule and make it a little bit more precise, make it a little bit more of a stepwise procedure.